Don is a happily retired engineer and project manager whose career in the offshore oil and gas industry took him to many places around the world. And he says some of them were even nice places to work. Since 2003, Don has been an avid amateur astronomer, astro imager, and HAS member. Studying the history and science of astronomy kept him well occupied and mostly out of trouble during his long stays away from home. But his real passion has been for astro imaging. Starting out with only a basic knowledge of photography, he has learned the ropes and become a competent astrophotographer and nightscape imager. After 20 years of learning the craft, he is still striving to complete that perfect astro image that knocks the socks off those who view it and wins multiple awards. Yeah, so it's always good to hear from Don and hear from what he's up to. So without further ado, please welcome Don Selle. Don, take it away.
Thank you. I'm going to share my screen here, and what Stephen failed to mention was the last little line on that bio. You know, I said in there that I really aspire to have that one awesome astro photograph, right? Well, it's good to have a dream. That's all I can say. Anyway, thank you for joining me here, and hopefully we'll take you on a little bit of a journey through interstellar space. I titled this "What Astronomers Need to Know About Nothing," because it's kind of interested me that, you know, we always tend to look at lots of objects, but when you really start looking at it, there's a whole lot more out there. It's just not really obvious. So let's get started. Let's go catch some. This is a story. It's not really beautiful out tonight, but when it is, we check the weather. We make an observing plan. We get everything organized. We go out to the HAS dark site, and we're going to go do some observing. So we're going to catch some set up and get focused. We're going to catch some photons. But when we do that, typically we're looking to observe lumps of matter in the universe. So when you think about it, all of the things that we amateur astronomers like to look at really are aggregates of matter. Our stars, the planets, the star clusters, galaxies, planetary nebula. It's all really lumps of ordinary matter. I want to make that clear up front that we're talking here about ordinary matter, and I'll tell you why in a second. What's between the lumps? Well, in between the lumps, it turns out that there's actually quite a bit. Most of it that we can't see. As we get out into the area past the solar system, turns out that there's quite a bit of material out there, gas and ionic matter, molecules, cosmic rays, magnetic fields, all kinds of things out there, most of which isn't really observable by amateur astronomers. It's called the Interstellar Medium, or ISM for short. So I wanted to make the distinction here. What we're talking about is ordinary matter and ordinary energy, okay? There's a reason for that. There's a big invisible elephant in the room, because there's much more to the universe than just the ordinary matter. And we're not going to talk about it much tonight, other than to just acknowledge it's there, because it is such a big part of the universe. The composition of the universe is really only about 5% of ordinary matter, ordinary energy. The bulk of it's made up, almost 70%, of dark energy and dark matter. Okay, those have cosmological effects, stuff that we can't see as amateurs, but we need to at least acknowledge that it exists. Ordinary matter is mostly hydrogen and helium, the constituents of the universe that were formed in the first few minutes of the universe, and about 1% of other stuff. But when we talk about dark matter, I'll just give you a real quick synopsis. Dark matter really kind of got its start at the beginning of at the end of the 19th century, the beginning of the 20th century, with Lord Kelvin. He happened to notice that some stars were moving differently than he thought they should, and he hypothesized that there was some unseen matter out there that was making it happen. French mathematician Poincaré actually took what Thomson did, corrected his math, but still didn't exactly get to the discovery. The real discoverer of dark matter was Swiss astronomer Fritz Zwicky. And in the study of astronomical history, he's a real interesting character. This picture of him here is one of those that's really very descriptive of the individual. He was a rather curmudgeon guy. He termed he came up with the term spherical bastard for anybody that he disagreed with or that disagreed with him. Spherical because it doesn't matter what angle you look at him, they're still a bastard, right? So, at any rate, fortunately, dark matter discovery. I mean, what Zwicky did is he looked at the galaxy clusters and realized that they were orbiting each other much faster than they should have, given the amount of bright matter. It took up until the 60s. Vera Rubin was one of the critical discoverers of the fact that galaxies themselves, if she and her partner in this, Kent Ford, they studied the rotation rates of galaxies. Basically, they looked at all of the edge-on galaxies, and they took spectra of them, and they could tell that the rotation rate of the galaxies, and they calculated that the galaxies should be flying apart because they were moving too fast, and that was really the observation of dark matter that convinced most astronomers that it actually existed. So, dark energy explorers. The dark energy really wasn't at all understood until much later in the 1990s. It came about with the advent of the oops, I'm sorry, I just messed up there. Dark energy came about, was discovered in 1998 when two teams of astronomers who were trying to measure the expansion rate of the universe using type 1 supernova realized that that it seemed that their observations showed that the universe expansion was actually accelerating. And that really wasn't part of the cosmology at the time. It was very surprising. We still don't really know much about what dark energy is. There's a lot of ongoing observational and theoretical work going on in this area. But the real discoverers of it were the teams. There were big teams that were doing this. Two of them were led by Adam Rees and Saul Perlmutter, and Brian Schmidt was one of the people that really pushed to get these teams put together, and he was actually part of the Saul Perlmutter team, but he had actually worked on both teams. But he pioneered the idea of the supernova searches. Okay, now back to the interstellar matter. ISM, what's it made of? I think you're probably seeing that this guy over here, aren't you? There we go. Got rid of it. Sorry about that. Interstellar media is made up of mostly neutral atoms. I mentioned earlier, primarily hydrogen and helium. Those neutral atoms are, especially of hydrogen, can be detected if you use the right method. There's also ions, and ions are atoms that have more they have lost electrons. They have more protons than they do electrons, and so they're charged. And the ions primarily that we see are hydrogen, oxygen O3, and sulfur S2. I mean, those are the hydrogen, oxygen, and sulfur. Those are the narrowband things that we astroimagers capture to make really interesting pictures. And there's also molecules in space. So when we talk about neutral atoms, H1 or H alpha is actually comes from a thing called spin flip spectral line. I'll get to that in a little bit more detail later as well. But when you look at the atoms, the abundance of them all, the ISM is made up mostly of hydrogen, about 91% hydrogen and about 7% helium. And the rest is just kind of, small parts of 1%. So when we talk about hydrogen, that again, it's really what started it all in the early universe, that and helium. So when you think about it, there are also a considerable number of molecules there in the ISM. At the current time, there are certainly that have been discovered for certain 235 different molecules, and probably about 40 or almost 50 additional molecules that have been kind of identified and maybe measured, but they haven't been proven yet. The vast majority of them are what's called organic compounds, molecules of organic compounds, because they're based on carbon chemistry. And the fact is that carbon, even though it's very rare compared to the amount of hydrogen in the interstellar medium, it's very reactive. And there are some organic compounds, some compounds made mostly of carbon, containing up to 19 atoms. And then there are actually two forms of carbon called fullerenes, which are strictly, you've heard of the term in the past, buckyballs. They have, it's a form of carbon molecule that takes 60 or 70 atoms. There's two forms of it that the carbon atoms bond with themselves in a great big clump. Okay, so that's the molecules. What about dust? Well, dust is actually pretty prominent in the interstellar medium, at least in terms of what we're able to observe. It's not, again, it's not a very large fraction of the interstellar medium, but it's very important to the interstellar medium, and in fact we'll get into it later. But it's very important to the formation of stars. Most of the dust grains are actually very small. They're made up of metals such as calcium, aluminum, and magnesium and oxygen, and they're pretty much the size of smoke particles. And in an interplanetary system, they can account for things like the zodiacal lights. But again, in and around star forming, newly forming stars and planetary systems, what happens is that these much smaller grains of dust tend to clump together and make bigger clumps, and those bigger clumps aggregate, and next thing you know, you've got small solar system bodies, and those end up becoming planetary bodies as well. So again, dust is really important, especially to we who live on aggregated dust in the solar system. So if we talk about the properties of the ISM, one of the things that we have to think about is how much is out there, how dense is it, and it turns out that that if you take an average of all of the particles in interstellar space and you measure it, there's about one atom for every cubic centimeter of space. So if you do the math, that means in a 1 liter bottle, there are only about 1,000 atoms, mostly of hydrogen. And if you think that 1,000 atoms kind of sounds fairly big, but if you realize that's more than 10,000 times better a vacuum than any the very best vacuums we've ever produced on Earth. So if you took a bottle of just regular atmosphere at sea level, there's 5 times 10 to the 22 atoms in that liter bottle. That's 50 billion trillion atoms. And if each atom weighed 100 grams, or about a half a pound, that bottle of interstellar gas would weigh 500 pounds. And a bottle of air would weigh as much as the Earth. That just, that's just trying to give you a sense of the scale. So the Milky Way, it turns out, is so vast, with only one atom for every cubic centimeter, that the amount of matter in the interstellar space in just the Milky Way makes up between 10% and 50% of the ordinary matter of the entire Milky Way galaxy. So it's just the fact that there are huge spaces between stars. The average space between stars in the Milky Way is something on the order of about 4 light years, between 3 to 4 light years between stars. And that's a huge volume. So when you have only one atom per cubic centimeter there, it doesn't take very much of that kind of vast space to add up to be a large amount of matter. It's about estimated to be about 10 to the 37 tons of gas and dust. And it's enough to gas and to create 10 billion stars like the sun. Just to give you an idea of the scale of the Milky Way galaxy, if you took all of the stars and planetary systems in the Milky Way galaxy and you compressed them down into a spherical volume with a radius the same as the distance between the Earth and the average orbit of Pluto, and I'm ignoring relativistic effects here. This is just a math problem, not an actual physics problem. It turns out that all of the actual matter, all of the stars in the Milky Way, would compress down into about a sphere about 8 miles in diameter, and that's with the whole Pluto average distance to the sun of almost 40 astronomical units. We'd have 8 cubic mile of diameter of all of the ordinary matter scrunched down to that size. That's about the size of the asteroid Gaspra, 951 Gaspra. So now that we've described a little bit about the interstellar medium, I'd like to give you a little bit of background on the history of the ISM. If you go all the way back to the ancient Greeks, Aristotle did a lot of thinking about the nature of matter, and what he understood as the universe basically was about the size of from the Earth out just a little bit past the orbit of the Moon. But one of his primary postulates is that nature abhors a vacuum. He could see matter moving around. And said every time there's a vacuum, stuff moves.
828,680.
So so as far as Aristotle was concerned, that there was something that had to be out there beyond the atmosphere of Earth and in between the stars. And he came up with the concept of a fifth element, the quintessence. And that had to exist so that no vacuum would occur out in space. Okay, well, quintessence kind of hung around for a long time. I mean, Aristotle's universe kind of ruled the worldview all the way up, at least into the Renaissance and a little bit beyond. By the middle of the 1600s, the idea of quintessence kind of morphed a little bit. It moved. It morphed into something called the aether, the ether. It was an invisible medium that was needed for interactions of certain large bodies. A little bit further on in history, it became the idea of a luminiferous ether, and it was proposed by Christian Huygens, I should say. And this became accepted science up until the early 1900s. William Herschel famously described holes in the heavens. There was a problem that the early observational astronomers saw. They knew that gravity would attract bodies to each other, and so it was like, how can we have all of these stars out there separate from each other, and the gravity not be pulling them together? And so in trying to understand all of that, Herschel observed quite a few what we now know as dark nebula in the Milky Way, and he proposed that they were actual holes in the stars through which we could see beyond the universe, because they assumed they understood the universe just to be what we could see in the Milky Way galaxy itself, and we could see beyond the universe and see the void beyond the universe. His son John also did quite a few studies of dark lanes in the Milky Way, and he is famously quoted as, "He is having swept well over Scorpio and have many entries in my sweeping books of the kind that you described." He's a letter to his father.
26,
Blank spaces in the heavens without the smallest star. That was 1835. So that was about where we could get to observing interstellar space up until pretty much the beginning of almost the beginning of the 20th century. So observing the ISM really took new technology that was developed first in the 1860s, 1870s. But before we get to that point, I want to make you aware that part of the reason why it took so long for humans to understand that there was something between the stars is because of the very limited windows we have had to actually observe the interstellar medium. if you think about it, this is a graph of the absorption of light in the atmosphere. The atmosphere at this level is completely opaque. Well, we have visible light in this area here, and if you look, you can't really see it here, but it's a pretty narrow window. We are able to get some infrared light in different bands, but mostly we are either observing the interstellar medium, the ISM, either with radio waves or with some type of spaceborne instruments. Okay, as far as the ideas of what's out there in between the stars, our ideas started to change, as I mentioned, in about the mid 1860s. This is when the very beginning of what's commonly called the age of new astronomy, new ways of looking at the stars were being developed, including photography and spectroscopy. The pioneer in stellar spectroscopy was Sir William Huggins, and in about 1864, I think it was, 1864, he measured the spectrum of a nebula. It was the Cat's Eye Nebula, if I remember correctly. So NGC 6543, which I think is, if I remember correctly, is the Cat's Eye Nebula. And he realized that he got bands of light that showed that it was that what he was observing was actually glowing gas. So he proved that there was gas in space. A number of years later, probably my hero in terms of observational astronomers go, Edward Emerson Bernard. He really spent a lot of time observing dark nebula in the Milky Way, and among other things, I mean, he was awesome. He found I've forgotten exactly, like 20 comets. He was a poor kid growing up in Nashville, Tennessee, and I'm sorry, I can see from my notes here he actually found 15 comets. He discovered his first at the age of 24. He discovered so many comets that he exhausted. There was a special prize that was given out, $250 for every comet discovered. He exhausted that the prize money by the time he was in his middle age. And because he was so good an observational astronomer, he was recruited onto the staff of Lick Observatory in 1897, and Vanderbilt University gave him an honorary degree. What's really cool about for me about Emerson is that he published. He took a large number of photographs. He learned photography from the age of 9 on, because he was working in a photographic shop. He was working for a professional photographer, and he did a lot of very wonderful things early in the 20th century in terms of producing some of the best astro images at the time. This is an example of one that is out of his atlas of selected regions of the Milky Way. There's 50 plates in there. It was published in 1927, about 4 years after Bernard died. But he was really trying to understand what was going on with these dark nebula. If I remember, it's like 360 different dark nebula that he cataloged. It's like 367 or 368, I forget which. Um, and this is one of my favorite. It's called, it's actually two, because he designated two. It's the Bernard's E. I always thought this was kind of ironic. E for EE, and it's there written in the stars. I recently took a astro image of the same area. It's actually Bernard Dark Nebula 142 and 143, and I took that earlier this year. And what's really kind of cool about this, I did the process to specifically to show as much structure in these dark nebula as in the dark nebula as I could, and also to show that as the dusk gets dimmer, you can kind of see that the stars in the background get redder. Okay, that's kind of important because another awesome observational astronomer, Robert J. Trumpler, actually confirmed that the interstellar extinction of starlight in 1930. He proved that what Bernard was supposing about dark nebula, that they really were some obscuring matter in front of the stars. Trumpler actually not only proved it, but he measured the effect. He was one of the first of the statistical astronomers out there, and that he took a large number of amount of data and analyzed it using statistical techniques. So in order to prove that there was an interstellar obscuring matter, he plotted the size and the brightness of 100 open star clusters that he observed. And when he plotted the two different things, brightness versus distance and size versus distance, the two graphs diverged. The two lines diverged dramatically, and he interpreted that as that there's something in between us and those star clusters, which makes the more distant star clusters look dimmer. He then turned around and did it using the spectra of the stars, and he showed that the stars actually got redder the further away they were. So not only did he prove that the interstellar matter, obscuring matter, was there, but that it made things redder as you got out further out away from the Earth. So modern observations of the ISM, as I mentioned, technology played a huge part in our ability to observe and understand the interstellar medium. Okay, as I mentioned, visible light, there's very limited windows. And what we've been talking about so far has been visible light observations, all the way from Huygens' measure of discovery of a spectrum of glowing gas, all the way up through Trumpler's proof that there's obscuring matter. There are some other things that are kind of interesting that have been done in the visible light. Modern visible light observations. There's still an ongoing, as far as I know, I think it's still an ongoing survey called the Wisconsin Hydrogen Alpha Mapper. Hydrogen alpha is a state of glowing hydrogen gas that we astrophotographers pursue pretty regularly, and it turns out that it's very visible. It's in a deep red color, and it turns out that this Wisconsin H alpha mapper has been in operation since the late 1960s, and their whole idea was to make a survey of the night sky and show where the H alpha is. It turns out that we also are able, with modern telescopes and astronomical cameras, we can actually image the dust illuminated by the starlight uh, around them, from around them. And where there's no stars, there's even a thing called the integrated flux nebula, where it takes very long. It takes very long exposures to show it, but and I'll show you a picture in a minute. This is the map of the distribution of hydrogen alpha that was done by the Wisconsin HA mapping survey. But the integrated flux nebula can be seen really well in the very north. This is Polaris. It's a picture that was made by an amateur astronomer. The integrated flux nebula was first imaged in 2004 by an amateur astronomer, amateur astrophotographer named Steve Mandel, and he saw these kinds of clouds around the galaxies M81 and M82, and they were kind of on previous survey plates, but it was really hard to tell. But when you did 10 and 15-hour integrations of the area around like Polaris, you could actually produce decent images of the dust clouds. Okay. Fortunately, there are other areas of the electromagnetic spectrum we can observe without besides visible light. One of them, the biggest hole in the Earth's atmosphere in terms of being able to pass electromagnetic radiation, is in the microwave area, radio astronomy. So radio astronomy actually started out in about the post World War II era. But before we get to that, I just wanted to show you this. These two are visible light. We have, or there's, I should say, ultraviolet light, which is Lyman alpha hydrogen. It's in the ultraviolet. The HA hydrogen alpha, which I talked about a little bit ago, it's the deep red, almost to the infrared. Those are visible through the atmosphere. But beyond that, we have to get into microwaves and radio waves before we're able to detect the hydrogen one, which is this. It's actually a thing called a spin flip. The proton and electron in the hydrogen, they both have a property called spin, and when they spin in the same direction, the hydrogen atom has one energy. When they flip the other way, the hydrogen atom gives off a little bit of energy over here, and it's in what's called the 21 centimeter radio band. So radio astronomy, as I mentioned, was a very key element in our understanding of what's out in between the stars. In 1931, Carl Jansky was a physicist and radio engineer, and he was assigned by Bell Labs to study radiostatic. It was one of the things that was really affecting radio transmission at the time, and Bell Labs wanted to figure out how to deal with it so they could increase the reliability of radio communications. And it turns out that what Jansky realize he had a very primitive radio dish, radio antenna. He found out that there was a regular pattern of the static. It rose and fell in a period of 23 hours and 56 minutes. And all of a sudden he realized that's the same period as one sidereal day, okay, which we amateur astronomers understand. It's not just, it's the rotation, 24-hour rotation of the Earth adjusted for the translation of the Earth in its orbit around the sun. That's why we have our constellations rise and set at different times every day, 2 hours difference a month, etc. So after World War II, the amateur astronomer and radio engineer, and I'm going to mispronounce this name. I think it's Reber. Matt could tell me this one better. So he because I believe he was Dutch. He took Jansky's work and using surplus radio equipment from that was sold off after World War II. He actually built his one of the first parabolic radio telescopes, and that got everything started. And again, radio astronomy has been this very essential in measuring the ISM and understanding it. So if you take this Barnard image that was taken in 1907, and you look at what was done with radio astronomy, you can see there's a definite correlation in the structures in the dark lanes and what's coming up with the distribution of hydrogen as well. So there are also other chemical elements like carbon monoxide that are detectable in radio frequencies, and things like come on, I'm losing this one. This is a ray in New Mexico. I can't think of the name of it now, but anyway, the synthetic aperture radio astronomy gets us to really fine
Are you talking about the VLA?
VLA, very large array. Thank you.
Yes,
I was just locking up on it. Thank you very much. I guess it's to very high resolution images of radio observations.
That VLBI, right? VLBI is the one where you use like the whole Earth.
Yeah. Yes. Exactly. But it's like. And there are radio telescopes that are distributed long distances apart, long baseline array is what I think you're talking about. There's actually one of those radio telescopes out in Fort Davis, right next to the Prude Ranch.
Yeah, I think it's very long baseline interferometry.
Yes, correct. Thank you. Okay, so 21 centimeter neutral hydrogen. This is a really nice picture of that. It's at 1420 megahertz, which is the radio frequency for neutral hydrogen. And anyway, there's been quite a bit of work done since this, but this was like the first really all sky version of mapping neutral hydrogen. Okay, so there's also, if you look here, we've got some little windows for infrared light. What's really kind of cool about this is that there's been a lot of very innovative ways to take advantage of those. Some are high in the mountains where there's very little atmosphere where the air is very dry. There's actually a couple of IR infrared observatories at the in Antarctica, because not only is it dry there, it's cold, and it allows the transmission of infrared very well, because infrared is also kind of like what we call heat rays, or there's a lot of heat transfer that's done by infrared radiation. Interestingly enough, William Herschel was one of the first to actually understand that there were quote unquote calorific rays, which was what he termed infrared radiation. That he realized he could feel the heat when he was splitting sunlight with a prism. Is that, hey, down here below the red, it's getting hot. The William Parsons, the third Earl of Ross, actually took a prism and detected IR light from the moon. And these early discoveries led to things like I was saying, airplane-borne infrared observatories way down south or up high in the Atacama Desert, and so on. Additionally, if we get, there were also balloon-based observatories that were getting up high enough into the atmosphere where they could pick up ultraviolet and infrared. And eventually those balloon-based observations led to the development of a huge array of space-based instruments that are able to look at infrared radiation all the way from the highest energy gamma rays all the way to the lowest energy radio waves. And this it's really been these space-based instruments that have really transformed our understanding of interstellar space and the interstellar medium. A couple of real key observatories like Galax and Spitzer, Planck, and WMAP. Not only have the Planck and WMAP, they were looking at early light from the universe, but in doing that, they were measuring a lot of infrared radiation that they had to account for and subtract out. So both Planck and WMAP satellites had infrared instruments on them so that they could correct their primary observations for the general infrared radiation that was around. Okay, well, I've given you an awful lot of background on what the interstellar medium is made of, but it turns out that in doing these observations, astronomers have actually realized that there's quite a bit of structure out there in the in the interstellar medium. So what are some of these structures? This chart comes out of, I got it out of Wikipedia, and it was a good summary, but everything from molecular clouds all the way down to what's called coronal gas, which is a hot ionized medium. They call it coronal gas because it's similar to what we see in the corona of our own sun. So molecular clouds, cold neutral medium, warm neutral medium, warm ionized medium, H2 regions, and coronal gas. It turns out that astrophysicists and physicists have modeled this stuff, and it actually works very well. The theory of gases that we use for lots of things on Earth actually works pretty well for analyzing the interstellar medium as well. So this is a kind of a illustration of our local neighborhood, and we have this what's called coronal gas, right? In this area here, it's very hot gas. We have 8,000 Kelvin gas and much cooler gas pockets, different areas around. Well, if there's so much of this, hugely, hot gas, 800 Kelvin is hot. This coronal gas is in the tens to hundreds of thousands of degrees Kelvin. That's kind of that sounds pretty nasty. So the question is, the temperature's a million degrees Kelvin outside, and so what if I'm out in the middle of that? Will my spaceship burn up? It turns out not so much. While you probably would if you were flying your spaceship through the corona of the sun, you would probably burn up. But that's more because of the intensity of the radiation coming from the sun at that point. Temperature is really a measure of the kinetic energy of a gas. Okay, and when you have the gas that's so sparse, it's such a low pressure as it is in the interstellar medium, that gas can be whipping around at a temperature of 1,000,000 Kelvin, but there's so little of it that you wouldn't hardly notice the effect on your body or on any of the things around you. So the answer is no. You won't burn up in the hot coronal gas in interstellar space. There's only one atom per 100 cubic centimeters where that hot gas exists. So it's very little energy to transfer from the gas to your body, so you won't get burned. Don't worry. This is another picture of the local area. We have the sun here in our local cloud, and there's also a thing called the G cloud, or it's another cloud of interstellar medium that is more towards the center of our galaxy. And if we went from our sun towards Alpha Centauri, we'd pass from our local cloud into the G cloud. So there's a little bit more about the structure of the ISM. And I have to say that this next slide is one of my favorites. It shows from the Keck Institute. It shows really graphically what you can expect. We have a medium here in our solar system, and we have what's called a heliosphere. And if you remember, Voyager spacecraft were heading out of the solar system, and they were using them in their later life to try and measure how far out this heliosphere went. And eventually they got to this point about 100 astronomical units from the sun, where they started to realize they were getting out into interstellar space. And what happens is you have solar wind pushing out, and there's actually a wind from interstellar space that's coming in the opposite direction, and it finally hits a point where the two actually cancel each other out. So you get a spot where there's no wind, and there's a transition zone. And then once you get through there, you're into the local interstellar cloud and into the Oort cloud. And now, as you get over towards Alpha Centauri, you're in the G cloud. And I really thought this was a cool illustration. So the other thing that we find in interstellar medium are giant molecular clouds, and uh, as I mentioned, there are like 240 or 250 actual molecules that have been certainly identified in the interstellar medium. Um, Carbon monoxide is one that's really good to observe. It's easy to see in radio astronomy, and it turns out that the mapping carbon monoxide gives us an idea where the giant molecular clouds are within our Milky Way galaxy, and it turns out that they mostly live in the plane of the Milky Way, where the stars are the most dense, et cetera. There's actually a reason for that, and we'll get to it in a minute. Here's another better picture from Planck, the distribution, Planck Institute, I should say, uh, um, galactic distribution of carbon monoxide. Again, you can see stuff kind of gets shoved up out of the plane, but for the most, it's concentrated right along the plane. So, examples of giant molecular clouds. Uh, we see one all the time. We observe one all the time as amateur astronomers, called the Orion Giant Molecular Cloud. And again, if you remember, the Horsehead Nebula is up in that area. Uh, um, the Orion Nebula is down in this area, and it's no surprise to find out that those are areas where they're part of that Orion Giant Molecular Cloud. Lots of dust, lots of gas, and it's actually the uh, these we know these giant molecular clouds are stellar nurseries, and the Orion GMC is the closest one to Earth. If you were inside of a giant molecular cloud, it's kind of like being in a really air polluted area. I mean, mostly because of the dust. Um, if the dust again with the size of grains of the dust are this about like cigarette smoke. You wouldn't see anything if you were on the inside. You could see stars close to you, but you wouldn't see anything outside of the cloud. No stars, no astronomy, no celestial navigation. And since at least here on Earth, the astronomy was the breakthrough to actual science. Maybe no science if you lived on a planet in a giant molecular cloud. Turns out that dust is really important in these giant molecular clouds, and I mean we see dust. This is the M45 or the Pleiades, and it actually is a reflection nebula. It turns out that the dust around the Pleiades star cluster is just the right size to reflect the blue light that comes from the hot stars in that cluster. And that whole area around there is just full of lots of dust, which kind of leads to this. I found this cartoon. Sure, it's beautiful, but I can't help thinking about all that interstellar dust out there. So, dust makes up about 1% of the ISM, but it's also spread pretty well throughout the Milky Way. And again, these observations are typically made using infrared because the dust takes other forms of radiation, other frequencies of electromagnetic radiation, and it absorbs it and re-radiates it in the infrared. And so you can see the big plumes above the plane of the Milky Way, but it's very dense in the plane of the Milky Way. And we've actually observed that dust through the infrared observation of another galaxy. This is M32, the Andromeda galaxy, and this is a depiction of the dust in there. And you can see, I mean, you can see the dark lanes, and it pretty much corresponds with those dark lanes. It's basically this was a Spitzer observation. They put together, it's a 24 micron observation of infrared radio waves, and they put together a big mosaic of the Andromeda galaxy to come up with this. I thought that would, just being an astrophotographer, I just thought that was a very cool image. Okay, dust in the interstellar medium. Because we already talked a little bit about the extinction of starlight and the fact that it causes starlight to become more blue. I mean, more red. It reddens the interstellar. It reddens the stars which shine through the through the dust in the interstellar medium. It turns out also that most of the chemistry that forms these molecules form either on dust grains or on grains of actual ice. There is water out in the interstellar space, and a lot of times it'll stick to the grains, and it forms a perfect place for chemistry to take place. And when you get into around a star formation, the grains stick together and make a protoplanetary disk. They grow larger objects, planetesimals. Next thing you know, the planetesimals are colliding, and you've got something that starts to look like a solar system. But as importantly, the dust acts as not just a catalyst, but it also cools. It cools the interstellar space. So this kind of gives you an idea of what goes on with these little silicate cores. They attract the molecules. This is the chemistry going on. But as much as anything, they scatter light. They transfer electromagnetic radiation from higher energy, re-radiate it as infrared, and cool the large molecular clouds, giant molecular clouds down. That cooling allows, you have this balance going on. You have gravity that's trying to collapse the cloud. The matter in the gravity attracts itself to itself, and it wants to collapse. Well, as that happens, the molecules and the atoms interact, and they start knocking each other around, and it's measured as an increase in temperature. The temperature goes up, and that prevents the cloud from collapsing. The dust then catches this heat, and it radiates it away at a much lower wavelength, and that helps the pressure to drop. Gravity continues to collapse the cloud. And then eventually, in most cases, gravity wins, and we have stars that are born. Stars shine, and stellar winds replenish the ISM. They blow the clouds away. They erode the giant molecular clouds due to the heating. And then the hot young stars die. They enrich the material in the interstellar medium, and shock waves from the death of those stars compresses the ISM, and it all starts over again. Compression, cooling, and the birth of stars. This is the pillars of creation. We also think of this as the Eagle Nebula. But what we're seeing here is these are pillars of dust in the interstellar medium, and it's kind of hard to see, but right out on the ends of these are little spikes that are sticking out where the dust is deep, and the density of the interstellar medium is very high, and this is where protostars form. So, again, we have the erosion of giant molecular clouds due to heating, and we see things like the Orion Nebula. There's huge amount of dust around the Orion Nebula because of the bright stars pushing them out. And then at the very extreme, we have the death of stars and the replenishment of the interstellar medium through nova and supernova explosions. And in fact, it's through these explosions, especially supernova explosions, where the heavier elements that we have in our solar system are actually created. A sun like the sun in our solar system will be able to produce elements maybe as big as iron. Beyond that, there's not enough energy to fuse the atoms to make that heavy elements heavier than iron. But that happens when you have a supernova explosion, which this is a remnant of a supernova. That's what happens. That explosion is so violent, it creates elements all the way out to the heavy radioactive elements. Mostly those stars just kind of die through either becoming brown, becoming dwarfs, or they eventually become planetary nebula and slough off their outer atmospheres, and a lot of them will leave behind a white dwarf star. So this kind of brings up the concept. Whoops, that slide. Here, let me get to the next slide because it's better. The birth and deaths of stars. It actually kind of lends itself to this cycle of birth, death, and rebirth. And I think this illustration kind of is very good at showing what it is. We have protostars forming out of the giant galactic clouds. Giant molecular clouds will get, if it's a mid-sized star, it becomes a red giant. A planetary nebula sloughs off a lot of its mass into this atmosphere. A lot of new chemicals are made in that, but it ends up as a white dwarf. Some go the red dwarf direction and back down, and eventually become black dwarfs. Very large stars, they go red supergiant like Betelgeuse, and eventually will explode. They very likely will form a black hole or a neutron star, and in the process, the heavy elements like gold and uranium and plutonium and so all of those heavier metals get formed in this explosion. So it really and truly turns out that the statement "we're all stardust." It's really kind of true, and that it's all part of this evolution of stars in the interstellar matter. And I just wanted to finish up with this little observation from E. Bernard. The Milky Way has always been of deepest interest to me. There is no work in observational astronomy that gives one so great an insight into the actual heavens as that of comet seeking. The searcher after comets sees more of the beauties of the heavens than any other observer. His telescope, though small, usually has a comparatively wide field of view and is amply powerful to show him most of the interesting parts of the sky. To him, the Milky Way reveals all its wonderful structure, which is so magnificent. And I think that's kind of sums it up for all of us, amateur astronomers as well. With that, I'll stop the share. And if you've got questions, let me know. I see one. Oh, very large array. Thank you, Brian. So if you have any questions, just come off mute and ask them.
Don, I had this question yesterday too, when Bill was showing, the gas that surrounds our Milky Way. But how do you guys know how far away this dust is? And I get the direction part. I don't get the distance part when this stuff is being mapped.
Okay. It's kind of it depends on what you're looking at, what you're trying to measure. Stars are probably the most easy things to measure distance to, because you have classifications of stars, and you know what their spectra look like, and you know what their how bright they or intensely they shine. So that being said, if it's all the way across the galaxy, and you're looking at a particular type of star, and you know those things, you can measure the intensity of that star and compare it. You do a calculation that says, okay, it's so dim over there. If it was at I think it's a 1 parsec is the standard measurement. That's its intrinsic measurement. What's the difference between the two? And I can get a rough idea of what the distance is. Now, I'm talking about dust and gas in between the stars, and we have to also take into account the dimming of starlight as it comes through that interstellar medium. There are other ways of doing it, like gas clouds. Again, you can kind of measure the rotation of the gas clouds, and knowing how far away they are, and what the radius is for that rotation. You can get an estimate of the distance from that. So a few things like that. But primarily it's star. There's a whole nother presentation I put together a long time ago. It's called the cosmic distance ladder, and it's really, you build on steps. I know how to figure out how far that star away is. Okay, now I have a star that's out there, and it's right next to something else. Right? See what I'm getting at? So
yeah, it actually makes sense to me for stars. It's just this interstellar medium that so it sounds like people figure it out because of what goes through the gas.
There's some of that. For example, starlight coming through the gas. You'll get a dark spot in its spectrum. Okay, the gas in between you and that star absorbs that frequency of light. Okay, depending on how fast that star is moving away from you or towards you, that spectrum line will be shifted slightly, and so you can measure how fast the star is moving by things like Gaia and observation and whatnot, and then you can also figure out from that how fast that cloud is moving, and do an estimate based on the speed of movement, how far away from, and angularly how it changes, how far away from you it is.
Okay, thank you.
I hope that it's not having been totally prepared for that, but it's kind of like that. I think at some point in time I'll dust that other presentation off and go through that maybe. Any other questions? All right, back over to you, Stephen, I guess, if you're there.
All right, Don.
Let me quit sharing.
Thank you for that. Thank you for that wonderful presentation, Don. It's always good to get some more info about our vast universe.